So in the first part of the second lecture, we're going to look at the phenomena of diamagnetism. Okay, just to outline, so this part, lecture 2A, is going to be about diamagnetism, and the second part of the second lecture, we're going to look at some aspects of the quantum mechanics of the hydrogen atom and how that can generate magnetic moments. Okay. So we previously introduced the concept of the susceptibility, the magnetic susceptibility. And this is defined, it's dimensionless, and it's the proportionality constant that indicates how much the material is magnetized in response to an applied magnetic field. So here I've got my B0, my applied magnetic field, and depending on the value of the susceptibility chi, it determines how big the magnetization response is. Okay, and somewhat alternatively, I can say that the magnetic field inside the material B is the applied magnetic field plus the fraction chi of the external field. Okay, so these two ways of looking at what the susceptibility is. Okay, the larger the susceptibility, the greater the magnetic response. And how do we distinguish a diamagnet? Well, so a diamagnet, when placed in a magnetic field, it tends to increase its energy. Okay, its energy is increased when it's placed in a magnetic field. So in order to minimize the energy, what does a diamagnet want to do? It wants to move to a region of lower field because its energy then will be lower. So in this diagram, which we discussed last time, you would see that the diamagnetic sample would move to the left to the region of low field. Okay, over here. What that means is that the susceptibility of a diamagnet is negative. Okay, so diamagnetic materials are defined by a negative susceptibility. Now, for most, in fact, for all ordinary diamagnetic materials, chi, the susceptibility is very small. So negative and very small, typically the order of 10 to the minus 6. Okay, so that means that the magnetic field that's induced inside the material is 1 part in a million of the applied field. Okay, so these materials are responding really quite weakly. Now, in the later part of the course, we'll talk about superconductors, but it can be helpful at the moment to realize that in a superconductor, it's a bit like a perfect diamagnet. Okay, it's one in which the susceptibility is identically 1. This would mean, if we looked at the previous definition, that would mean that the magnetic field inside a superconductor is 0, always, irrespective of what the external field outside is. Okay. Now, superconductors are a very special class of material. They're behaving quite differently, but it's useful to bear this in mind. Now, if this was a live lecture, I could have done a little demonstration for you, but actually, if you think about superconductors, one of the things that you may know about is things like maglev trains. The idea that a superconductor floats above a magnetic field, because what it's trying to do is it's trying to get away from the magnetic field. It's trying to get into a region where there is no magnetic field. And the force driving it to do that can be greater than the force of gravity pulling it down. And so it can be seen to float above the magnetic field. And of course, for something like a maglev train, that would mean you have a nice low resistance situation. Okay. Now, most diamagnetic materials, the diamagnetic effect is sufficiently weak that it's hard to notice the effect of the external field. The material that has the largest diamagnetic effect per weight is actually something called paralytic carbon. So this is carbon where it's mainly comprised of sp2 carbons, so it's quite graphitic-like, but it's not as perfect as graphite. There's lots of connections between the different layers. Okay, this has a reasonably large diamagnetic susceptibility, but we're still actually talking about the order of 6 times 10 to the minus 5, that type of effect. So it is really small, but we can make a sample that is sufficiently light that it will actually float above a magnet. And so these magnets here, so what I had to do, because I can't do the experiment in front of you, I've actually borrowed this from Wikipedia. And what we have here are some really strong magnets. So these are neodymium, they're rare earth magnets, more about them later. They're really quite strong. You do not want to get your fingers trapped in between two of those magnets. And here we have a piece of pyrolytic carbon. It's pretty light, it's very thin, quite low density stuff. And in order to move out of this really strong magnetic field to lower its energy, this sheet of carbon can be seen to actually float. Okay, so the upward force trying to get away from the magnetic field is perfectly balanced out by the gravity coming down. Okay. Okay. So how can we understand what is happening inside a diamagnetic material? And the first person to think about this was Langevin. And he did a purely classical description of diamagnetism in atoms. But it turns out that you get exactly the same result as if you do a full quantum mechanical calculation. Okay, I won't go through the derivation. I will just quote the result for us. Okay, and so what happens is when you place a material, in fact, any material with electrons in a magnetic field, the external field causes the electrons to move in orbits. Okay, they start to go, quite simply, they just start to go round. Okay, and what is this? Well, this is a magnetic moment. Okay, so if the electrons are going round in this direction, the current is going round in the other direction, so the magnetic moment will be this way. Okay, now Lenz's law tells us that the direction of motion should be to oppose the applied field. Okay, and that's why the susceptibility is negative. Okay, so actually we can understand this in a sense from the equations of classical electromagnetism. Okay, so if we've got a spherical atom, so a free atom, okay, that could be, it could be one of the noble gas atoms, or we could be imagining that a solid is comprised of spherical atoms. That's a reasonably good first approximation. It can be shown that the susceptibility of this is given by this equation here. So we've got our minus sign, that's the diamagnetism. N is the number of atoms per unit volume. Mu naught is just the constant. Z here is the atomic number. E is the charge on the electron, and M is the mass on the electron. Okay, the mass comes into it because we've got some orbital angular momentum here. The charge is also important. And what we have here is the average value of R squared. Okay. So this would enable us to calculate the susceptibility of an isolated atom. Okay. Now, all materials exhibit diamagnetism. Okay, so this phenomena of electrons having an induced motion around the nuclei will happen in all materials. Okay, even a ferromagnet, even a paramagnetic material. But it's a very weak effect. So if there is any other mechanism of magnetic response available, that other mechanism will dominate. Okay, so we only find a material to be diamagnetic overall if there's no other mechanism. Okay, so this will happen typically for materials that are closed shell. By that I mean all the electrons are paired up. Okay, so there's no spin density in the material. So for example, water, diamond, sodium chloride, noble gas atoms, all of those will be diamagnetic. Okay, but weakly so. So going back onto the theme of magnetic levitation, in case you've not heard this story, Andre Geim won the Nobel Prize a few years ago for his investigations of graphene. But a few years earlier than that, he won an Ig Nobel Prize, okay, which is given out for the kind of like crazy, unusual pieces of science done in the past year. And he won that in combination with Michael Barry at the University of Bristol. And what they did was they did some experiments backed up by some calculations and showed how a frog can be levitated in a magnetic field. And so if you do a YouTube search for frog floating in a magnetic field, that's what you'll find. Okay, so a frog, same as a human, is mostly comprised of water. Water is diamagnetic, so frogs are diamagnetic. You're also diamagnetic. Okay, so at the moment, you're probably, unless you're sitting in a magnetic box, you are probably experiencing the Earth's magnetic field. So what is happening is all the electrons in the atoms that make you up, they're all processing. They're all moving around their nuclei slightly and creating a magnetic field in you that is slightly different from the Earth's magnetic field. The Earth's magnetic field, luckily, is pretty weak, so it doesn't have much of an effect on you. But for the frog, Geim and Michael Berry, they put the frog above quite a large magnetic field, so the sort of magnetic field you might find in an NMR machine, 6 Tesla, 7 Tesla, that sort of thing. And the diamagnetic effect there is then appreciably large, and the frog, to lower its energy, it will rise above the magnetic field, and the force is great enough that it will overcome gravity. Okay. Now you might think, well, could we do this for humans? This could be an interesting kind of arcade thing. We could all go and float above magnetic fields. Well, of course, we're a lot heavier than frogs, so we'd need much greater magnetic fields. In fact, we need a very big magnetic field gradient in order for us to be levitated. And those magnetic field gradients would be probably very unpleasant side effects for us as humans. Okay, I don't think the frog is hurt because it's a much weaker magnetic field, but the sort of magnetic fields you'd need to levitate a human would do us some serious damage. Okay, so let's see some examples of this, of applying this equation. So we can use it, for example, for to predict what would happen in the series of noble gas atoms. And what is changing here? Well, the atomic number Z is changing, and the radius is changing because the mean value of the electrons is getting larger, and so the susceptibility, as we go down the periodic table, the susceptibility is getting greater in these materials. Xenon has a much bigger susceptibility than helium does. There's a few other things we can tell here. There's not really anything in that equation that depends on temperature. Okay. All of the constants at the front do not depend on temperature. R squared depends a little bit on temperature, because if we're thinking of a solid and we're thinking about thermal expansion, then that R squared could change a little bit. So we could have a slight temperature dependence, but to all practical purposes, diamagnetism is independent of temperature. Okay. If we wanted to apply this to a material, we would need to have some estimate of R squared. Okay. And that could come from a diffraction experiment. We could approximate it as being related to the interatomic distance. If we knew the wave function, of course, we could calculate R squared using what we know about quantum mechanics. Okay. So all these materials have the diamagnetic effect, but we don't always see it. This can actually be quite interesting because so many metals are paramagnetic. Okay, some metals are diamagnetic. We could never have a pure material that had zero susceptibility, one that didn't respond and didn't affect an external magnetic field. But we could imagine making an alloy. We could mix together a certain amount of diamagnetic, a certain amount of paramagnetic material in order to produce a composite that had no susceptibility. Okay, right. So let's now look at this is actually an exam question from 2017, and it said estimate the magnetic susceptibility of diamond. And we're told that the lattice parameter of diamond is 3.57 angstroms. Okay, so we're going to need to use the formula on the previous sheet, and maybe as a first approximation, we can estimate diamond as if it were a series of spherical atoms put together in the diamond lattice. Okay. So we need to start with the unit cell of diamond. Okay, so I'll have a go at drawing that. Right, start off with our outline of our unit cell. Okay, and let's see, so the unit cell length is A, and I need some atoms. So diamond is FCC, so first of all, put them in the cubic positions, and we need the face centers. Okay, and now we know, so that's FCC, but it's diamond, and so diamond has a quarter motif. So for every lattice point, we go a quarter away. So that's those 4 points. This one will be at a quarter. This one will be at 3/4. This one is at a quarter. This one is at 3/4. So there we've got our unit cell of diamond. Okay. Now we want to be able to relate the radius of these atoms, okay, to something about the unit cell. So if we look along the body diagonal, you should be able to convince yourself that there are 8 radii along the body diagonal. So that means 8 times, and let's associate this with the radius, and the body diagonal will be √3 lots of A. Okay, so this tells me that √3 to the half will be equal to, if I plug the numbers in, I get about 0.75 angstroms. Okay. What else do I know? I know that Z is equal to 6 because it's carbon. I know that the number of atoms, so sorry, N is the number of atoms per unit volume. Okay, so number of atoms per unit volume. And I can see that in this cell there are 8 and the volume is A cubed, so this is 8 over A cubed. Right, time to plug everything in. So I have that chi is equal to minus n mu naught z e squared mean r squared, I might have to write a bit smaller here, over 6 me. Okay. So this is going to be equal to, slightly smaller pen, okay, what have I got? Minus 8 on the top. On the bottom, I've got a 6. I've got my A cubed. Okay, 3.57 times 10 to the minus 10 cubed. Okay, I've got my 4 pi times 10 to the minus 7. My Z, which is 6. Okay, my E squared, 1.6 times 10 to the minus 19 squared. Okay. I've got my 0.75 angstroms. Okay, and what else have I got? I need to have the electron mass on the bottom, so I need to have 9.11 times 10 to the minus 31. And if I pop all that together, that gives me minus 3.49 times 10 to the minus 5. Okay, remember it's dimensionless. Now, interestingly, the experiment, if you look up the experiments for diamond, you will get minus 2.2 times 10 to the minus 5. Okay, and given that we were approximating diamond as uh, as spherical atoms, that's a reasonably good estimate. Okay, here's that written out a little bit neater. Okay, so this is as I said, diamond is probably an example where this works rather better. Other solids will be not quite so accurate, but often still the right order of magnitude. How could we do better? Well, for molecules, taking into account the bonding, formulas were derived in the 1950s and 1960s for how to calculate the susceptibility for molecules, so taking into account the bonding. Actually, calculating this for solids turned out to be quite a lot harder, and it's only really about 20 years ago that people came up with ways of calculating the diamagnetic susceptibility using what's known as first principles methods, so purely from quantum mechanics, and came up with formulas that were applicable to solids and could predict numbers that were in actually very good agreement with experiment. And actually, that was the work I did in my thesis about 20 years ago. So just to give you an example of that, so this is actually a molecule, but it's definitely not comprised of spherical atoms. This is actually an aromatic molecule known as porphyrin. It's very closely related to things like heme and also chlorophyll. And what you've got here is a magnetic field that's coming out of the page towards you. And the currents, rather than going around the actual atoms, this is a conjugated system, rather like sort of graphite. And what you've actually got here is are currents that flow all the way around the molecule. Okay, so here they do this. When they get to these junctions, sometimes they go around the outside as well. But you've got complicated currents that flow. So this is the same origin as the currents that Langevin was thinking about. This is diamagnetism. They're opposing the external field. But this is it generalized to how it can work within a whole solid. Okay, but as I said, you can get reasonably good estimates just thinking about solids as being comprised of individual atoms.